This first session, I will still try to do a couple of tutorials slowly, which are just plug and play, those that are already available, either on OpenFOAM's tutorial, like this one. This is provided by OpenFOAM, so I've just copy-pasted the folder from the tutorial folder, and now I'm going to run it. The second tutorial I want to do is about the boiling part, so we're going to do one of those one-dimensional problems that run just in a few seconds, and it's ready to run, so you don't need to do anything about it. So the first hour I was thinking to still be leading, the running the tutorial and stuff like that. And the second session, I was thinking to leave it open to you to practice. And in this slide, there is the immediate follow-up to this exercise 3 that I'm going to do now. Could be the one that I suggest, what I call exercise 4, which would be to achieve this kind of simulation where you get this bubble, like a gas bubble flowing from bottom of the channel to top due to gravity. And to do this tutorial, you need to, I'm explaining here in exercise 4 at the beginning how to start, where to get the files, what to modify, and then your task will be to modify it yourself. The tricky aspects are to create the geometry, to set the fluid properties. Then the case runs in 5 to 10 minutes, usually in one core. This is only 3,000 cells, I believe. So the second sessions, I would leave it for you to maybe try this exercise 1, this exercise here, or try to run the other boiling tutorials, or you can pick anything of what I have here, for example, on the day 4, which is about using some extra OpenFOAM functionalities. And so it's a bit up to you how you want to spend the second hour, the second session. I'm happy to move around and, see with you what you want to do, and maybe also do something that is not in the tutorial, but maybe you have an interest in trying to set up a specific simulation that is something that maybe we can do while we are here. For exercise 4, there is also the full case already available under OF training. So if you don't want to try to set it up yourself, you can just pick it up and run it. So for now, I would go back to our dam break case, because I was explaining the various files we have in the setup. So I go back here on the virtual machine. I have shown you block mesh dicte, which is the file to make the mesh. I showed you FV schemes and solutions, which is where you set up the discretization schemes and the solvers for the linear systems. I'm going to give you a quick look at decompose par dict. Here is essentially only if you want to run it in parallel. So number of subdomains is in how many subdomains you want to decompose your domain. So if you have a quad-core laptop, you can run it with 4 cores. If you are on a supercomputer, you can run it in how many cores as you want. There are different methods to run the decomposition. Simple is, as the name says, the most simple one, where you provide the number of subdomains in each direction. So 2 to 1 will decompose the domain in a 2 by 2 block. So very simple. It will try to decompose it in this way with two blocks on the x-axis, 2 on the y-axis, and allocate cells in a geometrical way. Typically, this is okay only when you have 4 cores. Typically, when you run it in a supercomputer, for example, you have 256 cores, you may want to use the alternative, which is Scotch, which is another decomposition method where you don't need to tell anything to OpenFOAM. OpenFOAM will not look at these numbers you give here, but OpenFOAM will find the best way to allocate the different domains so that all the processors, they have more or less the same number of cells. But here I'm just going to go back to the way the file was before. And now setFieldDict is the file where we initialize the DOM. So you remember, this is the setup we want to initialize. We want to have essentially this rectangle here on the bottom left. So we cannot input this rectangle under 0/alpha.water. That file is only to give 0 everywhere or 1 everywhere. But we can use setFieldDict to initialize a rectangle of water in this exact location here. Now, we need to give the coordinates of those vertices. Here is where OpenFOAM, for some reason, becomes a bit counterintuitive and not always too smooth. So, you can impose different geometries. Box to cell is to impose a rectangle. You can have circle to cell, cylinder to cell. You can have different shapes. You can initialize. You can do Boolean subtractions and to have a bit more complex shapes. But the way box to cell works is that you need to give only 2 sets of coordinates. We have 0, 0, -1, which identifies a point, and these other 3 numbers that identify the 3 coordinates of another point. So the way setField works is that, let's say this is the shape we want to initialize, and because OpenFOAM is in 3D, we need to make it 3-dimensional. So I'm going to make it 3-dimensional in this way. And the coordinate axis will be y, z, x. And the coordinates OpenFOAM wants while setting up this set field coordinates are, let's say, the lowest in the 3 coordinate direction. So, for example, this one is 0, 0, -1. Let's say this coordinate would be in 2D 0, 0. Let me talk about the third coordinate later. And the highest in all the 3 coordinate directions. So with only these 2 points, you have fully identified a 3-dimensional box. So 0, 0 are the coordinates of the bottom left of the red box. Then you need to give the coordinates of this point, which in this specific case are given down here, and they should be 0.1461 meter is the x. The y seems to be 0.292. So this should match what we have in set fields. Yeah, that's correct. So what about this z coordinate? I said before that the domain is always in 3D in OpenFOAM. So let's take a look at BlockMeshDict. The depth of the domain in BlockMeshDict goes from z equal to 0 to z equal to 0.1 multiplied by the scale factor 0.146. So in meters it would be from 0 to 0.0146. So let's say that it would probably be somewhere here, the domain. Now it's a bit difficult to make it on this graph, but the z depth of the domain is very tiny. So what do we put in z in these 2 coordinates? What OpenFOAM will do will be to set alpha.water equal to 1 to all the cells inside this box. So along Z, this box can be infinitely long as it's thicker than the domain. We need to give a fixed domain size along Z, and it doesn't really matter which value you give. I usually give a small domain size along Z just so that in paraview it looks quite two-dimensional, the geometry. Then this box to cell, you can give minus 10 power 9 plus 10 power 9. It doesn't matter as long as it's thicker than the actual extension along Z of the domain. So in the specific case, the tutorial is set from -1. So the tutorial is actually giving -1, which is fine because the domain, the lowest Z extension of the domain is 0. So the box will actually go until -1. And the top Z coordinate of the box is +1. So it's actually +1 and not plus 10 power 9. So the box will go along Z between -1 and 1, the water box. The domain in reality is much thinner, but we don't really care. What we need to make sure is that the box is thicker than the domain so that all the cells within have a value of 1 for alpha.water. If you had a 3D domain, a real 3D domain with 3D cells, then you wouldn't have this problem. You would give a meaningful value of the Z coordinate. So with set fields, we get alpha.water 0 everywhere and alpha.water equal to 1 within a box with these coordinates. At this point, sampling now it doesn't really matter for us. The last file I'm going to show you is control-dict. This is the management of the simulation. So application interform is the solver you're using. Start from start time 0 means that OpenFOAM will start the simulation from a folder named 0. That's why it's looking for a folder named 0. If we had start time 1, then we should rename our folder 0 as 1, because OpenFOAM will look for that. Stop at end time 1. So OpenFOAM will carry on the simulation until it gets to 1 second. Delta t is the time step, so 10 power -3. Write control adjustable, write interval 0.05 means that OpenFOAM will save the results every 0.05 seconds of simulation time. And because the simulation runs with an adjustable time step, the time step will change during the simulation. So the delta t 0.001 is the time step it will use only at time step 1. After which, the time step will change to maintain a current number of 1. So the current number, you can imagine it as a ratio of the fluid speed and the size of the cell. So a current number of 1, it means that the fluid moves 1 cell in 1 time instant, which is a bit too much for a volume of fluid. Basilisk uses 0.5. So in any meaningful simulation, I would suggest to use a value much smaller than 1. But OpenFOAM is set also to try to work with higher current numbers if the two-phase flow simulation works well. But still, even with a variable current number and variable time step, OpenFOAM will try to save the data every 0.05. So it will adjust the time step at the right moment in which it needs to save data. Purge write 0. Purge write is a command to delete folders as the simulation runs to avoid having thousands of folders. Purge write 0 is not doing anything. If you put purge write 5, for example, OpenFOAM will save first time folder 0.05, then 0.1, 0.15, 0.2, 0.25, which is 5 folders. When it saves 0.30, it will delete 0.05. When it saves 0.35, it will delete 0.1. So it tries to maintain always maximum purge write number of folders to avoid overloading your memory. Write format ASCII and write precision 6 is the format of your result. So they will be saved in ASCII format with 6 meaningful digits. Write compression off. If you set it to on, it will compress your result files to save some time, to save some space in your memory. So they will all have an extension .zz, which is the Linux extension for a gun-zipped file. Time format general, time precision 6 is only about the name of the folders where it saves the results. So time format general, it will save the result into folders called 0 point time step, or even above 0 if you are at a higher than 0 time step, than 1 time step. Time precision 6, if the time step it wants to save has some digits, it will use maximum 6 significant digits. Runtime modifiable yes means that you can come in here and modify this file while the simulation is running. So you may want to change your time step, frequency of saving of data, and you can do it by changing this file and OpenFOAM will reread it. Adjust time yes is about variable time step. And this part here include, I'm not going to talk about it, but it's to do some runtime post-processing that is specified in the file sampling, which is a file provided in the tutorial. Now, I'm going very fast in explaining all these things, but in the slides, every single entry of every file is explained hopefully in a bit more detail. Yes?
The time is dimensional right now.
Sorry?
The time
Yeah.
is dimensional.
Everything is dimensional in OpenFOAM, yes. Yeah. So everything is in meters and seconds.
Okay. So the time step we impose
It's also a dimensional value. Yeah, yeah. So I'm now going to go through the steps of running a simulation because this one is simple, everything is already prepared, we only need to run it. So the steps we need to take are, we should run the utility called block mesh that will generate the mesh. Set field will initialize the volume fraction field based on the entries in set field dict, and block mesh will generate the mesh based on the entries we have in block mesh dict. After which, I'm not going to look at the decompose part for now. We will simply run interFOAM, which is the name of the solver we are using. So this pipeline of commands is always the same for all OpenFOAM cases you want to run. So I'm going to start with, you need to go under dump break, make sure that you are in the location where there are all the folders. And now I'm going to type block mesh. If everything goes well, you get no error message, and the output on the screen, you can check that everything looks reasonable. For example, here you have the bounding box of your domain. So imagine this is a box which is perfectly fitting your domain. Number of points, well, I don't know about number of points, but number of cells, maybe you know beforehand how many cells to expect from your domain, so you can double check that. And these are all the patches that have been created while running block mesh. Left wall, right wall, lower wall, atmosphere, and default faces. You can at this point take a quick look at ParaView, ParaFOAM with uppercase F. Now, here my problem is that everything is ridiculously small in terms of letters and icons, but this is the domain, and you see the domain along the Z direction is much smaller than X and Y. So for now, you can just look at the domain and look at the mesh. So now it's extremely small, but here I'm going to look at surface with edges to be able to see not only the surface of the domain, but also the edges of the mesh. So we see that in the z direction, there is only one cell. X and Y, there is the mesh that we have created. Now, I've not gone into the details of the mesh, but it was a mesh with uniform cells everywhere, except in some regions, due to the way the domain is made. But the first sanity check you usually do is take a look at your mesh to make sure that everything looks correct. And the next step is set fields. Well, I could show you that, for example, if I plot, here there is nothing to plot, because there is skip 0 time, which is this very small icon here, enabled, so it will not read any folder named 0. Now, I'm going to click on that because I don't want to skip 0 time. I want to see what I have in 0. So now ParaView is looking at the 0 folder. This is the alpha field, which is this is the velocity magnitude. Alpha water is blue. You cannot see the number, but I tell you that this is 0 everywhere, because that's the boundary condition we have input. That's the initial condition we have input. We haven't run set fields yet. So alpha.water is 0. U is 0 because we set initial velocity 0 everywhere. Pressure is also 0 everywhere. Here, ParaView is simply reading within your 0 folder, is looking at all the alpha.water, PRGH, and U. So now, I keep ParaView open. Let's run set fields. So if everything runs correctly, set fields will tell you that is setting the internal values of the volume scalar field alpha.water and is setting values to 1 within this box with these coordinates. So if I now go back to ParaView, I need to do a bit of a refresh and update of ParaView unless you just close it and reopen it. And now alpha.water is there. So let me do it without interpolations. So you see that now alpha is 0 everywhere except in the box that we have defined. And we see that the box goes through the entire domain. So the initial condition has been correctly set. If the water box is there, then you're ready to start the simulation. So you can type interFOAM with uppercase F. Yeah.
When we use ParaFOAM,
Yeah.
how we go back to the user line?
Yeah, that's a trick.
It's Control C. No.
So you do Control Z to free the shell. Then ParaView gets blocked. You need to type BG, which stands for background, and enter, which means that the process will be put in background. So ParaView can be used, and at the same time you have freed the terminal. Otherwise, you should open just a new terminal and repeat everything. So interFOAM, this will run for a few seconds. In my laptop is quite quick. It gets to time 1 in 3-4 seconds. And at every time step, OpenFOAM is telling you what is happening. So we have Pimple is is a combination of simple and piezo, which are the typical pressure velocity coupling algorithm to couple momentum equation solution and Poisson equation for pressure solution. So smooth solver is solving for alpha dot water. You get the initial residual, final residual, and number of iterations. So always make sure that your linear system for alpha is solved until below the residual tolerance within a number of iterations you are expecting. After which, I look at this line here where we are solving for pressure. So the pressure velocity coupling is done with 3 pressure correctors. So that's the reason why you see this line here repeated 3 times. Second time, third time. So the first time, at the first corrector loop, you see the residuals are not going down too much. They go from 0.35 to 0.001, probably because of the settings we have chosen. So if I look into system FV solution, is using this relative tolerance of 0.05. So it will solve pressure only until the residuals are only 5% the initial value. It's going to do that at all pressure corrector iterations except for the final one, PRGH final. It takes the same settings as PRGH, but with 0 relative tolerance. So it will only look at the absolute tolerance in the last corrector loop of the pressure velocity coupling. So that's why residuals fall only a tiny bit in the corrector 1, another tiny bit in the corrector 2, and eventually in the corrector 3, the last corrector, the residuals go below the tolerance, which was set to 10 power minus 7. So you see the number of iterations are growing from 2 to 18 to 49. But it's useless to have 49 iterations from the first one. You only want to update your solution a bit and then do a last loop of big correction. What has happened now in the dump break file, in the dump break tutorial? Many folders have been created, one for each time it has been saved. So within every folder, there are files that will be read by ParaView. For example, if I open alpha.water at 0.5 seconds, what is inside alpha.water? It's just a big vector with all the values of alpha.water in every cell of the domain. You cannot see it here because it's a bit cut. Let me move it to the right. So 1, 1, 1, 1, 1, and then 0.99. These are all the values of alpha in different cells of the domain. ParaView will know how to allocate each value to the right cell. ParaView knows it because ParaView will look into constant, polymesh that now is being created once I generated the mesh, and then points. These are all the coordinates of your mesh. So ParaView will combine the result file with polymesh to allocate at every point of the mesh the right value of the solution for visualization. So if now I refresh a bit ParaView, we should be able to see the column of water falling. So we saved every 0.05 seconds, which means 20 times in 1 second of simulation time. So if everything goes well, you should be able to see gravity pulling down the water column and water splashing around. So I don't know if anyone has been able to try it. If you have any error, I can help you. Yeah? To update? On the left, I typically click on refresh. There is a box called refresh. You don't have the... Yeah, I can come over and take a look. Yeah, can you see it? Break. So you have the folders here. It seems simply not updated. Go to ParaView, and we don't need to look at the pipeline browser. But it's missing a menu. Maybe it's better if you close it and reopen it. Sorry, on the black band. Double click. Yeah. And open this tiny line here. So now you can see it. The only weird thing is that I don't see the menu. Yeah. Do you mind if I play a moment with your mouse? Understand if it's a resolution?
Yeah, no, but maybe, yeah. I can't do this. Yeah, it's impossible. Oh, I need to see.
So you can see it now. The problem is that there's no real reason there is no menu on there. Yeah, so maybe try googling ParaView pipeline browser because it's very strange that it doesn't show at all.
I figured that out.
It's working now? Okay. Yeah? Mm-hmm. Yeah. Yeah, yeah. Yeah, I think I will. We'll go ahead finishing the tutorials in this hour, and then the next hour everyone can work maybe on the exercise that I proposed. The second case I had in mind, and then I'm happy to switch everything off and just work with you on the tutorials, is one about the evaporation case. And I'm going to quickly show you the one-dimensional Stefan problem in which we have the one-dimensional domain with the left side covered with vapor. The right side will be covered with liquid, and heat is coming from the left side. So heat is coming from the left side, and our interface is supposed to move to the right because liquid will evaporate. And this was the setup we have seen before. And now I'm not going to go into the details of the solver, but essentially it has, because we are solving also the energy equation, we have some additional parameters to set. I'm simply going to run the tutorial and look at the results and look at the way we also make sense of the results. So now, the folder is not available by default under OF training, but is available under the solver folder. So if I go under solvers and then boiling foam public, under cases, there is multiple test cases. I'm going to look just at Stefan problem. So I'm going to do copy this folder and place it under run. So now we have Stefan problem here. And we can simply run it by typing / or run, which will execute all these steps here. You can run them manually, like we did for the dump break, or you can use the all run file, which is what you usually do when you get a bit more practical. And looking at the various steps that we are doing here, we have block mesh again. The only extra complication is that now we are using boiling foam, which is a multi-region solver where you can have fluid and solid. And minus region fluid is just to tell boiling foam to only make a mesh on the fluid region. It needs to be there even if you have only a fluid region. Then the initial folder is going to be called 0.03, and this is just because we want to compare with the analytical solution, but we start with a one-dimensional domain where we put already vapor at a certain distance from the wall, but the analytical solution is for the interface staying at the wall. So if this is time and this is location of the interface, the solution goes this way, and we are already starting with a certain x initial, and at this x initial we have a time initial which is 0.03. So we want to start our simulation from this point here, and we are just going to tell OpenFOAM to call the 0 folder, call it 0.03, so that then it's easy to compare the result with the analytical solution. Otherwise we should shift it, but this way is a bit easier. A couple of new utilities we haven't talked about, actually only one, set field from table. Besides set alpha field that we have seen before, set field from table is to, for example, get data to initialize your simulation from a file. So you remember before that I was saying that there will be a thermal boundary layer developed on the liquid side of the interface. So this is vapor, and this is liquid. So we want to make sure that at the time 0, we are getting the initial temperature boundary layer correctly here. And that initial temperature boundary layer was calculated previously with another solver and is put into a table that will be used just for the initial conditions. All the rest is just the same as we have seen before. Run application $get application will run the solver that is indicated in control dict. And Python 3 should only run do the comparison with analytical solutions. So there is a Python script within this file, Stefan problem. There is a folder called Python and a Python script which is analytical. No, that's the solution already. Plot benchmark. So this is a Python script that when you run it will compare the simulation result with the file called analytical.csv, which is already available here. So this takes, it's very quick to run. So if I just type /all w run, you see the sequence of commands being executed. Now it's stopped after ICO-boiling-foam because it's actually running ICO-boiling-foam, which is the solver. So it may take a minute or so, whereas block mesh, set field from table, they were all quite quick. So once it's done, it should move to the last line in our run, which was the comparison with the analytical solution. And it will spit out the comparison of the two. You see that the analytical solution is the blue one that starts from 0. The simulation starts from 0.03. And they evolve quite in agreement with each other. You can potentially carry on the tutorials for the phase change part and do the sucking interface and vapor bubble growth. The vapor bubble growth, the way it's set up, should run quite quickly, like in 10 minutes or so. And if we look at the result of the Stefan problem, just in ParaView, so here we are looking at the volume fraction field at time 0. So we see that the part on the left is vapor. The interface is located in this cell here that is colored between blue and red. And the right-hand side here is liquid. If we look at the temperature field, there is still nothing here because this was the time 0. If I move up one time step, now we see that the interface has moved quite a few cells from here at time 0 to the new time. We can see the temperature, so we have a much hotter wall and the temperature is decreasing until it reaches the interface. And if we look at the velocity, we can see that the vapor is not moving, is at velocity 0, and the liquid is moving with a uniform velocity to the right. And this is due to the fact that there is a certain density ratio between liquid and vapor, and there is actually, in the easy case of a one-dimensional simulation, there is an easy way to calculate what that velocity would be, and I reported here in the slides, let's say, which observation to take from this test case. But essentially, the liquid is supposed to move faster than the vapor, and the velocity of the liquid is proportional to the rate of evaporation. So if we start looking at all the time steps, we see that over time, we can look at the interface moving from the beginning to end. And we can also see the velocity of the flow, that over time the interface moves to the right, but the velocity slows down because, if you remember well, the interface moves with the square root of time, which means that the velocity at which the interface will move will evolve as 1 over the square root of time, derivative of the location of the interface. So over time, the velocity of the fluid should decrease. So I think I've said more than enough all in one shot. What I would suggest you to try to do now, either depending on what are your interests, either you try the other tutorials for phase change that are available there, or I can recommend you to maybe try to put your hands on exercise 4. So in exercise 4, we want to study this problem of gas bubble rising in a liquid field channel with no bulk motion. And I'm providing here the parameters to use in terms of domain width, fluid properties, and surface tension. And the domain box this time is much more simple, so it will be just a box with 8 vertices. I suggest using 40 cells in the x direction, 320 in the vertical direction, with a certain n time max current number. These are the boundary conditions I recommend. So you can really just take the dam break file and modify what needs to be modified. You will need to, the things that you will need to modify are the mesh and the geometry. And I suggest taking another file from another tutorial to do that. Everything is explained in the slides. And you will need to impose this rectangle of gas within the domain to start your simulation that looks very much like the rectangle of water that we initialized before. So in slide 72, I have all the steps suggested to take. So assemble a new folder by taking the dam break folder and just renaming it. And for the block mesh dict file, you can take it from another tutorial, which is from the capillary rise tutorial. And you may need to tweak a little bit only the coordinates of the vertices, otherwise all the rest remains the same. You can follow these steps here, and hopefully you should be able to try to set up the simulation and run it. It takes 5 to 10 minutes to run it. It may take about 1 hour or so to set it up yourself, because there are a few elements that you need to be careful of. If you don't want to wait, the files are already available in the OF training folder.